We had gone through in the previous video the derivative function for square root of x. There was a problem with the derivative of square root x. It didn't exist at 0. And so we asked this question, well, what's stopping the derivative from existing at 0? Now, to understand that question, we have to understand what it means to be differentiables. Algebraic understanding of that just means, look, if I have this definition, mathematically what that means is, okay, if your function is differentiable at a point, this limit exists and it's two-sided. If we just stopped there, we'd miss very deep intuitive understanding. You really get to understand what this definition means by thinking about things graphically. So what we need to do to understand differentiability is to understand the secant slopes. If you have the function x squared, it's a parabola. So you could come up with the derivative function, 2x. If, for example, I said f prime of 1, it would be 2 times 1. So if I were to go to the point 1, draw a tangent line, its slope would be 2. F prime of 0 would be 2 times 0. And so that would be this line right there. It would have a slope of 0. So the tangent line exists. What does it mean for that tangent line to exist? And this is built into this two-sided nature of the derivative. If you were to take some points to the right of that and draw a secant line, as you start moving the points closer and closer together, they start becoming flatter and flatter and approaching that purple line. Now, at the same time, the limit is two-sided. So that means you have to be able to draw secant lines on the other side, regardless of whether you're on the right or on the left. Both secant lines approach the same, and I'll put it in brackets, tangent line. And if you observe this behavior, the function can make a decision about what the tangent line is at your point. And that means that the tangent line exists at the point x equals 0 and that the function is differentiable at x equals 0. And so this two-sided interpretation of that definition has a really useful intuitive meaning. Pick a point. If you think its derivative is going to exist, you have to be able to build secant lines on one side, build secant lines on the other side and move them closer, and they have to match. Both secant lines have to agree on what they're going to end up on. Now, earlier when I gave you the function absolute value of x and I said, what's the derivative at 0? It didn't exist. If I were to take the same approach as I did above and pick a point to one side and move that point closer and closer, we had calculated the secant slopes on the right side have a value of 1. But if I go to the left side and I calculate the secant slopes, regardless of which point I pick on the left, all of the slopes want to be -1. The function is confused because it can't decide what secant slope to choose. And as soon as the function can't agree on the secant lines, it can't be differentiable. So since the secants can't match at x equals 0, we say that the tangent doesn't exist. And because of that, if the tangent doesn't exist, then the function is not differentiable at x equals 0. So to be able to really give you a nice way of visualizing this in your head, this is an important theorem. If a function is differentiable at a point x equals a, then it is continuous at that point x equals a. My goal is to try to show that when I take the limit of my function as x approaches a, that it equals the value of a, because that's the definition of continuity. The only thing that I have to work with is that this function is differentiable. So that means that whenever I calculate this limit, it must exist. We are going to build up. I am going to consider this limit. Now, I don't know what the function is, so I'm limited in the kinds of algebra that I can do. So the only algebra that I can do is add 0 or multiply by 1. Here's the first 0 that I'm going to add in. And then what I'm going to do is group these together. And so the next stage is going to be for me to say, okay, I'm allowed to multiply any piece of this by 1. So I'm going to choose to multiply that first piece by x minus a over x minus a, and I'll have this by itself. And I would love to know if the limit laws can apply. This is a constant, so its limit exists. This is just some polynomial, so its limit exists. And we are told that f is differentiable, so that means this limit exists and it equals f prime of a. And so at the end of the day, it is very much possible for us to use the limit laws. And what's going to happen is that this part will give me an f prime of a. This will give me a minus a, and that last part is a constant. A minus a is 0, so this whole term is 0, and all I'm left with is f of a. So I have just shown you that if I take the limit of this function, I get an f of a. So that means f is continuous at x equals a. There's a lot of value in understanding what this theorem says. It says that if a function is differentiable, the function must be continuous. If you can draw a tangent line at your point, it means your point cannot have holes, gaps, jumps, or breaks. There are some rules to what are called conditional statements. It turns out that something called the contrapositive is also true, which means that if a function is not continuous, it is then true that the function is not differentiable. If your function has a hole, gap, jump, or break, it cannot possibly be differentiable. And you have to be careful. Something called the converse is not always true. What is the converse? It's when you switch the order. If a function is continuous, does it mean that the function is differentiable? Not always. And we have an example of this. The function absolute value of x has a picture. This function absolute value of x is continuous everywhere. There are no holes, gaps, jumps, or breaks. But f prime of 0 does not exist. It's not differentiable. So just because a function is continuous doesn't mean it's differentiable. The contrapositive result is very important. If your function is not continuous, so for example, if it has a removable discontinuity like this, could you find its derivative at that point? The answer is no, it's not possible. Well, why not? If I were to take secant lines and move them closer, as I get closer and closer here, the slope wants to go to infinity. On the other side, as I take secant lines and I move them closer and closer to that point, the slope wants to go to negative infinity. Either way, the slope does not exist and they don't match. F prime of a cannot exist. Another example of a function that is discontinuous is something with a break. If I wanted to know whether or not I have a tangent line at the break, I would do the same story. I'd pick points and I'd take their secant lines and move them closer. As I moved them closer and closer, the slope would go to infinity here. On this side, the slope would exist, but they don't match. And if they don't match, that means f prime of a cannot exist. If we come back to our square root example, we can try to figure out why f prime of 0 didn't exist. As I pick secant lines and I start moving them closer and closer, the slope of that secant line goes to infinity as I approach 0. The slope is undefined. Infinite rise for no run. And that means that f prime of 0 cannot exist. And so essentially, if a function cannot have matching secant lines, you cannot have a derivative. That could happen when your function is not continuous, as I've shown in this. But even if your function is continuous, it may not have a derivative. This example here was something that I'll call a corner. You have non-matching finite slopes. A corner is an example of something that is not differentiable. You could have an example of a function where you've got a point like this. This point, the slopes of the secant lines just don't agree. And furthermore, the slopes would go to either plus or minus infinity. This is what I would call a cusp. This is where you have non-matching secant slopes, but they're infinite. The example with the square root here, the tangent line wants to go vertical. So when you have a vertical tangent line, the derivative cannot exist there. So to sum this all up, when you have a graph of a continuous function, I said to you it has no holes, gaps, or breaks. If a function is differentiable, it can't have any holes, gaps, or breaks because it has to be continuous to be differentiable, but just being continuous is not enough. It can't have any corners, can't have any cusps, can't have any vertical tangents. Somebody once said it in another semester, no pokey things. Any sudden change in the slope is bad. Which functions have tangents? Well, it's ones that don't have any holes, gaps, jumps, or breaks, and no surprises in their slopes.